Okay, so welcome back. We had a very long break. So many of you have had exams. I don't know how many exams you had. Maybe we will have a little bit of chit chat at the end just to catch up. Yeah. So most of you may be taking 4 or 5 courses, and at least 2 or 3 exams you might have had. I don't know. We will talk about it. So we will start Riemann mapping theorem today. I will not finish the proof. I will do it in 2 classes because I don't want to do too much today, and I also want to talk about other things at the end. So we will try to save some time, but let's start the proof today. So Riemann mapping theorem, if you recall, we want to say that any simply connected, we had this characterization of simply connected regions. We had some 9 equivalent characterizations, and we proved everything except one, which is that if you we wanted to say that having any non-vanishing holomorphic function admits a holomorphic square root. This is equivalent to the region being simply connected, right? So one way we showed, if the region is simply connected, you can non-vanishing functions admit a holomorphic logarithm and therefore a holomorphic square root. But if every non-vanishing holomorphic function admits a holomorphic square root, we did not show that it is simply connected, which is what we will do today, and that's part of Riemann mapping theorem. Okay, so most of what we have done till now, we will be making use of in order to prove this result. So I think last time we did Schwarz lemma and some applications of Schwarz lemma, and those ideas will be used today. And the class before that we did normal families and Montel's theorem. Those ideas also will be used today. And in order to finish the proof, which we will not do today, but in the next class, we will use open mapping theorem, we will use Montel's theorem, we will use Roche's theorem. So we'll use all these things. Yeah. And today we will use Schwarz lemma. I mean, some applications of Schwarz lemma which we have done. Yeah. So that's all that we need. So let's start. So I should share my screen. I've kind of forgotten how to do all these things. Yeah, share screen. Yeah, open share. Desktop. Could you please confirm you can see this?
Yeah, I can see the screen.
Yeah, and my sound is also audible enough, no, as usual?
Yes, sir.
Yeah.
Good, good. I think we had a 2 weeks break, so it's like a fresh starting for me. Everything, seems new. Okay. So I think our last class was September 30th. Today is October 16th, so 2 weeks are over. Yeah. So there was your mid-sem break 1 week. Before that, there was Gandhi Jayanti holiday. And after that, I said I will not be teaching one class. So all put together, it became 2 weeks. Okay. So today, lecture 16 and RMT is our topic, Riemann mapping theorem. As I said, we will not finish it today. We could have finished by going a bit faster, but I thought since we are meeting after a long break, I don't want to rush. I also thought we should have 10-15 minutes at the end just to talk about your last week's experiences regarding mixing. Okay, so we will do Riemann mapping theorem. So we had a long break. Yeah, okay. So these things are part of the slides. We met on September 30th. I hope your exams went well, if at all you had exams. In the last class, we discussed Schwarz lemma, and I think I left it as an exercise to do the Schwarz-Pick lemma. And Schwarz-Pick lemma. And Oh, by the way, I'll just briefly mention those interested, we can talk at the end. So you know that I have this habit of Googling for names of these mathematicians. So Pick, it's George Pick. And I was Googling this and I was searching about him. And it led me to a very new book which I just bought. I haven't read it. I haven't started reading it, called Einstein in Bohemia. Which so Einstein knew Pick very well. It was a much senior mathematician to Einstein, and many interesting things. Maybe I'll put one or two tidbits from the book in the future slides. Let's see. So Schwarz-Pick lemma. This is what we did. Schwarz-Pick lemma I did not prove. I asked you to prove, or I asked you to check the Wikipedia page, which has a good proof. These were basically applications of the maximum modulus theorem, and we computed OT U. What is U? U is the open unit disk, and automorphisms of U, these are of the form phi alpha given by Z minus alpha by 1 minus alpha bar Z. So I told you that phi Z equal to AZ plus B by CZ plus D. These are called Mobius transformations. So Z minus alpha by 1 minus alpha bar Z is a particular kind of Mobius transformation. And these are the automorphisms of U, meaning bijective maps from U to U. Holomorphic inverse is also holomorphic. Biholomorphic maps from U to U. And Z minus alpha by 1 minus alpha bar Z, can alpha be any complex number? Do you remember? What was the condition on alpha?
We took alpha to be within U itself.
Yeah, mod alpha is strictly less than 1, alpha is in U. So these are the biholomorphic maps, and we computed this. So these were certain type of Mobius transformations. In the class before that, we did Montel's theorem. We had done Montel's theorem about normal families. So very quickly, what is a normal family? It's a collection so that every sequence has a subsequence that converges. And as we said, the limit need not be part of the family. That we are not asking for. And so this definition had nothing to do with holomorphic functions. And the famous theorem here is Azila-Oscoli theorem. The main part was, right, you recall this diagonal process and all that we have done. And the main part was what? You had to assume two things and you will conclude that it is normal, family is normal. And what were the two things that you assumed? We had introduced equicontinuity. So you have to assume family is equicontinuous, and one more thing, some boundedness, right? So I think we assumed, what did we assume? Locally point-wise bounded? Can someone just quickly confirm? In Azila Oscoli, we conclude that the family is normal, point-wise bounded, right?
Yeah, I think so.
The family is
point-wise bounded plus equicontinuous implies normal.
Equicontinuity, yeah. So we had to assume point-wise boundedness and equicontinuity, and we did this diagonal process. Yeah, so if you were talking about some general metric space, then you have to assume separability, meaning there is a countable dense subset so that you can start the diagonal process. And then you conclude that it is normal. Yeah, so what is normal? Once again, earlier I missed a keyword. Normal definition is the family is normal if every sequence has a subsequence that converges uniformly on compact sets. That's part of the definition, uniformly on compact sets. So this we did, and then we did Montel's theorem. And Montel's theorem, if you have a collection of holomorphic functions on a open set on a region, holomorphic functions, collection of holomorphic functions, we wanted to conclude, appealing to Azila Oscoli, that it is normal. But you need to assume something, and we assumed locally uniformly bounded. What does that mean? Given a compact set, it is uniformly bounded on that compact set. And we did not assume equicontinuity. Equicontinuity we proved using Cauchy integral formula. Yeah. So if you assume locally uniformly bounded, and because the functions are holomorphic, We did some complex analysis and concluded equicontinuity and appealed to Azila, Oscoli. And if I remember, we had to do one more diagonal process, whatever, those are technicalities. We concluded that, yeah, we use compact exhaustion, right? We use compact exhaustion, and we had to do a further diagonal process on this Kn contained in Kn plus 1 contained in, etc., and concluded that a locally uniformly bounded collection of holomorphic functions is normal. So this we have to use today, not today, tomorrow, and in the next class. Okay, so we had done Montel's theorem. Today we will do RMT making use of all these things. Not just these things, we will use open mapping theorem, we will use Rouché's theorem, we will use Schwarz lemma, yeah, all these together. It's a very nice proof. Let's see, yeah. So suppose omega is a simply connected region, as we have observed before. If omega is the whole of C, then it cannot be holomorphic, biholomorphic to the open unit disk. It will contradict Lewis theorem. So the statement is that if it is a proper region which is simply connected, then it is biholomorphic to the open unit disk. So omega is contained in C, it is strictly contained in C. Omega is not equal to the whole of C. Okay, so we want to show that there exists a holomorphic function from omega 1 to 1 in omega on to U. This is enough, right? Therefore, it's a bijection, and such a function has an inverse, and inverse is automatically holomorphic, right? We don't need to show anything more. Why is that? So if you have a bijective holomorphic function, then the inverse is automatically holomorphic.
Because the derivative is never zero.
Yes, we have
So
done this.
locally we have all that.
Correct. This is inverse function theorem. So we have done this. Maybe I called it towards OMT or something. That was local. Inverse function theorem was local, but derivative is non-zero is what we use. So if the function is 1, 1, then derivative is non-zero everywhere. So at every point there's a neighborhood on which the inverse is holomorphic, and holomorphicity is a local property. So it's holomorphic. Inverse is holomorphic everywhere. Okay. So this is what we have to show, that there is a 1, 1 function on omega on to U which is holomorphic. Okay, for this, standard approach in many of these things, we are going to consider the collection of all the functions holomorphic on omega and 1 to 1 in omega and images contained in U. So we are going to start by considering a family of functions, a collection of functions, sigma, capital sigma, which is all holomorphic functions psi on omega. I don't know whether this notation is used in analysis. In algebra, we use this, right? To show that it's injective, I put a hook here. Anyway, what I meant is injective, whether this is standard or not. So psi is 1 to 1 in omega and contained in U. I'm not saying it is on to. I want to show that there is such a psi which is on to. So consider this collection. Okay. And we should show that there exists some psi in sigma which is on to. This is what we need to show. So you consider this collection and you have to exhibit an element. You have to show the existence of an element in the sigma which is also on to. Now there is a long-winded way of doing it. As you will see, it's a very beautiful proof. It's not at all obvious how to do such a thing, but we are going to do it. So first of all, why is this collection non-empty? Right? In order to show that there is a function which has this extra property, it's also on to. First of all, you have to show that this collection is non-empty. There are such functions, and then we will show there is one which is on to. So let's see that sigma is at least non-empty. So that's what we are going to do first. So pick a W0 outside omega. Why is it possible? Because omega is not the whole of C.
Omega is not all.
Correct. Because omega is not whole of C, so you can pick such a W0. So pick one and consider the function Z minus W naught. F of Z equal to Z minus W naught. What can you say about this function on omega? On omega, this function is never zero. It is non-vanishing throughout. So it's a holomorphic function, non-vanishing throughout omega, and therefore, because omega is simply connected, we already know that every non-vanishing function has a holomorphic logarithm, every non-vanishing function has a holomorphic square root. It is a holomorphic square root that we use in this proof. We will use it once here, we will use it again. In the next argument also we will use it. Okay, this is claim 1, this is non-empty. Then we will have a claim 2. Here we are going to use non-vanishing functions will have holomorphic square root. Once again we will use it. So this is the first use. It's non-vanishing and therefore has a holomorphic square root. So this we know because it's simply connected. Call it phi. Okay, so phi is the holomorphic square root of this function z minus w naught, and z minus w naught is non-vanishing because w naught is outside omega, and such a w naught exists because omega is not the whole of c. So call it phi. And note that phi is 1 to 1. Why is phi 1 to 1? Because phi square of z is z minus w naught, and z minus w naught is of course 1 to 1. So if phi of z1 is phi of z2, then phi of z1 square is phi of z2 square. So z1 square minus w naught is, no, z1 minus w naught is z2 minus w naught, therefore z1 is z2. So phi is 1 to 1. Same argument also shows that if phi z1 is minus phi z2, then also z1 is z2 because you are squaring, so minus sign will go. Right? If phi z1 is either phi z2 or minus phi z2, then the square is z1 minus w naught. On the right hand side, square is z2 minus w naught. Therefore, z1 equal to z2. By the open mapping theorem, you know that phi of omega is open because omega is open. So phi of omega is open. So I'm using open mapping theorem here. I have to use open mapping theorem again much later in the next class. Okay, by OMT, phi of omega is open. Therefore, it contains a disk. Let's call it a DAR. So a disk centered at A, some small radius R. This is completely contained in phi of omega. And I'm going to choose R small enough. In fact, R less than mod A will do. So that DAR and D minus AR, I'm taking another disk D minus AR. These two disks do not overlap. These two disks are separate. Okay, so if R is less than mod A, this will happen, no? DAR is somewhere and minus A will be diagonally opposite somewhere. And if R is less than mod A, then these two disks will be separate. So do this. What is the aim? Aim is to show that sigma is non-empty. I want to exhibit an element in sigma. So that will be 1, 1 function on omega holomorphic and valued in U. Image should be contained in the open unit disk. So this you can do. And we conclude that this is a claim. D minus AR does not intersect the image phi omega. See, DAR is contained in omega. DAR is contained in phi of omega. This contains phi of AR, and D minus AR I have chosen away from DAR, and we claim that D minus AR itself does not overlap phi of omega. No. D minus AR does not overlap DAR, and we are concluding much more that D minus AR will not intersect phi of omega. Why? Because otherwise, if you choose a Z2 here, which is also Z2 in omega, so that phi of Z2 is also in D minus AR, then minus of phi Z2 will be in DAR, right? D minus AR. So minus of phi Z2 will be in DAR, but DAR is a disk inside phi omega. Okay. And this implies there is a Z1 in omega with phi of Z1 is minus of phi of Z2, right? Minus of phi of Z2 is in phi omega. Therefore, there is a Z1 in omega such that minus of phi Z2 is phi Z1. But if this happens, then Z1 is Z2. That's how we constructed this phi. So Z1 is Z2. So phi Z1 is minus phi Z2 is phi Z2. That means phi Z2 is 0. So Z1 equal to Z2, and that's a contradiction since phi is non-vanishing on omega, right? Phi was, why is phi non-vanishing on omega? Because its square is non-vanishing. The function Z minus W1 is non-vanishing, therefore phi is also non-vanishing. But this contradicts, right? If Z1 is Z2, then phi Z1 is phi Z2, but phi Z2 is minus phi Z2, so phi Z2 is 0. That contradicts phi is non-vanishing on omega. Phi is non-vanishing on omega because phi is the square root of this function, and this function is non-vanishing. So phi square is non-vanishing, therefore phi is non-vanishing. Okay, so you have proved that d minus ar intersection phi omega is empty. Now what you do is define the function psi to be this radius r, the constant function r divided by the function phi plus the constant function a. You have chosen a DAR, you have got a and r, and take r by phi plus a. So because phi of omega does not intersect d minus ar, phi plus a. Phi plus a will never be 0, right? Because phi of z plus a is 0 means phi of z is minus a. But that cannot happen. This doesn't intersect. So this is well defined. Division by phi plus a is okay. And now note that what is the modulus of this? Modulus of this is strictly less than 1. Why? Because first of all, let's see that modulus is less than or equal to 1. Because otherwise, so modulus strictly less than or equal to 1, meaning r is less than or equal to phi plus a. Otherwise, phi plus a is strictly less than r, and phi plus a is strictly less than r, meaning modulus of phi plus a is strictly less than r, meaning phi minus minus a is strictly less than r. That will contradict this. Phi of omega, right? Phi of z minus minus a is less than r, meaning this intersects, but this does not intersect. Therefore, this modulus is less than or equal to 1. But you would like to say that the modulus is strictly less than 1, but that's okay because both these things are open, right? Phi of omega is open. So even on the boundary, uh, right, if the modulus is equal to 1, then you are getting a point z such that phi of z is on the boundary of this. But that also cannot happen because phi of omega is open, right?
I think we directly get the strict inequality, right?
Are we getting directly?
Yeah, because we have that mod of phi minus minus a
Yeah.
is strictly greater than r. Acha, no, okay, no. Greater than or equal to. We have to
Greater than or equal to, no? Yeah. But anyway, it's the same idea because of openness on the boundary also you cannot have a common point. Yeah. So this is valued in U. So observe that psi is 1. Yeah, and also psi is 1 to 1. Why? Because phi is 1 to 1 and these are constant functions. So C is 1 to 1. So not C, psi is 1 to 1. And it's valued in U since P omega is open. And I think you're using this. Otherwise, it doesn't matter. If you're getting directly, good. Otherwise, use this. Yeah. So it's 1 to 1 and valued in U, but the collection of 1 holomorphic functions valued in U is what we call capital sigma. So we have exhibited a function in capital sigma showing that capital sigma is non-empty. So this is the first claim. So at least the collection that you have started with is a good collection. It's a non-empty collection. Non-empty reminds me of something. I mean, I was not thinking of saying all this because I wanted to save time. But let me say it because this happened just before the class started. I was searching online and quickly let me ask you, how many of you know about Leo Tolstoy? Yeah, I
Was he
mean,
an author?
yeah, famous Russian novelist.
Yeah,
I've heard about
I've
him,
heard
no?
of him. Yeah.
And many others also must have heard of him, no? Can one or two people quickly say? Tolstoy is so famous. Someone else?
Yes, sir, I have heard of him.
This is Preetham.
Yes, sir.
Okay, good. Have you read any of his books?
I have read The Naked King and one or two other. I currently don't remember exactly, but
Okay, good. And you know this, I mean, maybe his most famous book is War and Peace and also Anna Karenina, right? And
yeah,
Karenina.
yeah,
I am
yeah.
taking so much time, and this opening sentence is very famous. This book I have read, and the opening sentence, how do I get this? Maybe it's a very famous quote. See, it's suggesting all happy families are alike. So, yeah. Can you see this, or should I zoom further? Can you see this?
Yeah, it's visible.
Yeah. So all happy families are alike. Every unhappy family is unhappy in its own way. This is the starting sentence. So it's a very, very famous sentence. The reason for my saying is when non-empty came, I remembered this because mm, so there's this mathematician in the US somewhere, and just before this class only I saw this. Can you see this? This is today. So 2:47 a.m. US time maybe. Can you see this? So he paraphrased it. Empty sets are all alike. Every non-empty set is non-empty in its own way. Just, mimicking the starting sentence of an academy. Yeah? All of you can see this, right?
Yeah.
Yeah, okay. Anyway, a digression. Uh, yeah, that was just before the class started. I was just, browsing the net and I saw that and I liked it a lot. Yeah. So, okay. So, this is set is non-empty. Yeah. Next, we make the following claim. We are going to see what do we need to show. Keep in mind our final aim is to show that now that we have showed sigma is non-empty, we want to exhibit a function in sigma which is also onto. Okay, that's our final aim, which we are going to do only in the next class. Let's make the following claim. If psi is a function which is not onto u, then we isolate a property. So if psi is a function which is not onto u, then for any z0 in omega, whatever you pick any point in omega, and we are going to exhibit a function psi1 in sigma. So you are taking a function psi, and suppose it is not onto, suppose it is onto, then you are done. You want to show that there is an onto function. So if you take a function and if it is not onto, then whatever point you take, I can find a function psi1 such that the derivative of psi1 at z0, its modulus, is strictly bigger than derivative of psi at z0. Okay, so this is going to be the next claim, and you will see why this is going to play a role. Okay, so yeah, so let's prove this. And do you can you get a feeling that Schwarz lemma kind of technique will be used here? Because if you remember, we proved Schwarz lemma and then we proved what Rudin calls an extremal problem, right? If you have a function f and if you compose it with phi alpha and phi beta on either side, where f of alpha is beta, then we proved that modulus of f prime alpha, we got a bound. I think it was mod of f prime alpha is less than or equal to 1 minus mod beta square by 1 minus mod alpha square. We proved such a thing using Schwarz lemma. So such an idea is going to be used here in order to exhibit this psi1, in order to construct such a psi1. So let's do this. Okay, is the statement clear? If psi is not onto, then whatever z0 you give me, I'm going to show that there exists a psi1 in the same collection sigma such that its derivative at z0 modulus is strictly bigger than modulus of psi prime at z0. Okay, so let's do this. And observe that this is not zero. So there's no, this kind of strict inequalities are okay because psi prime z naught is never zero. Why is that?
Because
All these
you're
things are
taking it
not
1 to 1.
Yeah, it is 1 to 1. Therefore, it's never zero. So since I is 1 to 1 in omega. So we'll use ideas involving Schwarz lemma. So this I think was a very next section in Rudin after Schwarz lemma. Again, existence of holomorphic square roots. Already we used it in order to show that sigma is non-empty. We use the existence of holomorphic square roots. Once again, we are going to use that in a very different setting. Okay. So let psi be in sigma and assume it is not onto. And because it is not onto u, there is a point alpha in u minus psi of omega. Agree? It's not onto you are assuming. Therefore, there is such a point alpha. Now what you're going to do is you compose this psi. So psi is a function which is 1 to 1. I have put a hook here, 1 to 1 to u, not onto. It is given to be not onto. And you are going to compose this with a map from u to u. You know automorphisms of u. They are phi alphas. So you're going to compose with such an automorphism, a phi alpha from u to u, given by, this was the definition of phi alpha, right? Phi alpha means z minus alpha by 1 minus alpha bar z. So you compose. So u to u, you have phi alpha. So phi alpha composed with psi you consider. You agree that phi alpha composed with psi is valued in u because it is this together with u to u. So that's valued in u. And phi alpha is a bijection and psi is 1 1. So the composition is also 1 1. So phi alpha composed with psi is another element in this sigma. And this is non-vanishing on omega. Why is this non-vanishing on omega? Phi alpha composed
Because
with,
it's never alpha. Because it misses alpha.
because it misses alpha, exactly. Because of this construction, because it misses alpha. So phi alpha composed with psi of this thing is never alpha. And only at alpha this can vanish. So phi alpha composed with C is non-vanishing. Now you know what we are going to do, right? What are we going to do now? Take its holomorphic square root. So there exists a G in H omega such that G square is phi alpha composed with psi. Yeah, existence of holomorphic square root for an everywhere non-vanishing function. Since G square is valued in U, right? Phi alpha composed psi is valued in U, therefore G square is valued in U. G is also valued in U. G is from omega to U. G is anyway holomorphic, it's valued in U. Since G square is 1 to 1, G is also 1 to 1. Right? Therefore, what is the conclusion? G is a holomorphic function 1 to 1 valued in U. In other words, G belongs to sigma. So you have constructed a function G and sigma in this fashion. And now we are going to compose this G with phi beta, where beta is G of Z naught. Remember, you're given me some point Z naught in omega. And corresponding to that Z naught, I'm going to choose a psi prime. Psi 1, psi 1. So I'm going to compose this G. So you have composed with a phi alpha, taken its holomorphic square root, and further compose it with phi beta, where beta is G of Z naught. Okay, so alpha information which is outside the image is already used in phi alpha. The given point Z naught I'm going to use here by taking beta equal to G of Z naught. Since beta is in U, right? G is valued in U, so beta is in U. We have phi beta compose. Phi beta makes sense. Phi beta is an automorphism of U because beta is in U, and phi beta composed G is in sigma, exactly like earlier. Now this is my psi 1. Psi 1 is phi beta composed with G. And now what do we need to show? We need to show that psi 1 prime at Z naught modulus is strictly bigger than psi prime at Z naught. Given psi, you did this, you got a G, and you took this beta and you did this in order to get psi 1. So given psi, given Z naught, you have gotten a psi 1, and the claim is this psi 1 will do the job. Psi 1 prime at Z naught modulus will be strictly bigger than psi prime at z0, the modulus. This is a clue. So let's do that. This is where the Schwarz lemma idea will come. So we claim that modulus of psi 1 prime at z0 is strictly bigger than modulus of psi prime at z0. So towards this, remember the extremal problem. By extremal problem, I mean this. I think this was Rudin's word. If you have a function f from u to u, and if you have alpha and beta such that f of alpha is beta, then phi beta composed with f, no, then f prime alpha modulus is less than or equal to 1 minus mod beta square by 1 minus mod alpha square. Maybe I'm recalling it. Yeah, I'm recalling it in the next line. So for a and b in u and for f from u to u holomorphic with f of a equal to b, we had shown that modulus of f prime a is less than or equal to 1 minus mod b square by 1 minus mod a square. You remember the proof? What we did is you compose f on one side with phi minus a or a, I don't remember, and the other side with phi b or minus b. One is minus and the other is plus. I think it was phi b composed f composed phi minus a. And this function you can apply Schwarz's lemma. See, Schwarz's lemma, you also need f of 0 is 0. So that may not be given here, but by composing like this, you get that condition and then you apply Schwarz's lemma and mod of f prime 0 less than or equal to 1 for that function f, and from that you can conclude this. Phi a and phi b, anyway you can compute the derivative because there's an explicit formula. So that's how you prove this, and this we are going to use. So now we are going to consider capital F to be alpha and beta are there. No, what is alpha? Alpha is a point outside the image, u minus psi of omega. Alpha is a point there. And what is beta? Beta is g of z0, where g square is phi alpha composed with psi. So you have phi beta, phi minus beta, and phi minus alpha. And what is the function s? S is just squaring. S for squaring. S of z is z square. That's a function. So consider this capital F, which is phi minus beta, which is from u to u. Then consider the function s, which is squaring. That is again a function from u to u, and compose further with this. So f is a function from u to u. S is squaring. And in this formula, take f to be capital F and a to be 0. What do you get? You will get capital F prime at 0 modulus is less than or equal to 1 minus modulus of f of 0 square divided by 1 minus mod 0 square. So you will get, so take b to be f of 0, which happens to be psi of z0, but we don't need that. So modulus of f prime 0 is less than or equal to 1 minus mod f0 square. That's what you will get here. Okay. And I'm saying
B
this
is beta and A is alpha, right? Everywhere.
Huh?
B is beta, right? Like earlier we had said beta.
Yeah, but this is something else that I am stating from the last class, no?
Okay.
So that's why I changed A to alpha and B to beta, because this is some general fact that I have stated here from last class. Okay, so therefore I deliberately put some two other things.
But
And
in the next line, this alpha is...
yeah, I think you are right. So I'm coming there by thinking parallelly. So this is fine. And this alpha and this beta are the correct alpha and beta. Alpha is outside, alpha is from u minus psi of omega, and beta is g of z naught. Now this is also okay. I'm just saying in this formula, take a equal to 0 and b is then f of 0. So this is fine argument. I'm just saying apply in this formula f to be capital F, a to be 0. That's all that I'm saying in this formula.
Okay.
That's okay.
But then the next B in the same line,
Yeah,
that
b
has to be beta, right?
0. B is by definition f of 0.
No, it's capital F you're writing, and you've taken psi also. So
My small f is capital F.
right, but the psi is...
No, that's also okay because it is f of 0. No, so apply 0. I'm just saying f of 0, this is irrelevant. This we don't need. That's in brackets. But even if you want to check it, it is just taking f of 0. I'm just saying f of 0 happens to be this. F of 0 is phi minus beta of 0. So what is phi minus beta of 0? That will be beta, no? That will be beta. So S of beta will be beta square. Beta square is g of z naught square. G of z naught square. But g of z naught square is phi alpha composed psi. And you are composing with phi minus alpha. So this is psi. This is psi at z naught. So that's it. No problem, no? This is just evaluating, which is irrelevant. But because I was here, I just evaluated it just like that. That's all.
Okay.
I can even delete this. This is not required, but this is true anyway. Agree, Ariman?
Okay, yeah.
Yeah. But because the formula was there, I just thought of evaluating. It is not required for us. Okay. So the point here is, why is this strictly less than 1? See, it is 1 minus a positive quantity, and therefore it is less than or equal to 1. I mean, it's a non-negative quantity, therefore it's less than or equal to 1 is clear, but I'm saying it's strictly less than 1. It is the very next line is the explanation, but you want to think about it? What happens otherwise? Suppose it is equal to 1. If that is equal to 1, then what is the meaning of that? Then f of 0 is 0, no? If this is equal to 1, then f of 0 is 0. So capital F is a function where you can apply the original Schwarz lemma because it takes 0 to 0. And Schwarz lemma has two parts, and the derivative part says if you have a function f of 0 is 0, then mod of f prime 0 is less than or equal to 1, and equality happens if and only if equality happens precisely when f is a scalar multiple of the identity function, right? F of z equal to lambda z with mod lambda equal to 1. So if equality happens here, if it's equal to 1, then f of 0 is 0. And mod f prime 0 equal to 1. That will force capital F to be a multiple of the scalar multiple of the identity. That will force capital F to be a 1-1 function because it's a scalar multiple of the identity function. So capital F will be a 1-1 function, but capital F is not 1-1 because squaring is involved. Therefore, it's not 1-1. Right? So strict inequality is because if mod f prime 0 is 1, then f of 0 is 0 from here, and therefore by Schwarz's lemma, f has to be a multiple of the identity function, in particular 1 to 1, which it is not. Which it is not because of the formula for f. Not 1-1 is clear, no, because of squaring. So you can exhibit 2 points where the image is the same. So you have to take 2 points as that phi minus beta of z equal to minus phi minus beta of z. If you do that, then the square is the same. So those 2 points you will get the same value here. So it's not 1-1. Okay, so you have considered this capital F, and what you have shown is modulus of f prime at 0 is strictly less than 1, strictly less. And this is enough to show our claim. So recall that our definition psi 1 is phi beta composed g, and recall that g square is phi alpha composed psi. Therefore, psi is what? Psi is phi minus alpha composed with squaring of g, but g is phi minus beta composed with psi 1. Agree with this? Psi is phi minus alpha composed with g square. G is phi minus beta composed with psi 1, then squaring of it, S is squaring, and then phi minus alpha. This is psi. But this is the function that I call capital F. This is the function that I call capital F. This one. Phi minus alpha S phi minus beta. Phi minus alpha S phi minus beta. So this is capital F composed with psi 1. Apply chain rule. So beta is G Z naught, and note that psi 1 at Z naught is 0. Why is that? Why is psi 1 at Z naught 0? Because psi 1 is this, beta is G Z naught, therefore phi beta is 0 at beta, no? Phi beta is z minus beta by something. So at beta it is 0. So beta is g z naught. Therefore psi 1 at z naught is 0. So apply chain rule to this equation. You will get psi prime at z naught is f prime at psi 1 of z naught, which is 0, times psi 1 prime at z naught. And you are done, because mod of f prime 0 is strictly less than 1. So you have shown that mod of psi prime z naught is strictly less than mod of psi 1 prime at z naught. That's what we wanted to show. Okay, so Schwarz lemma ideas is used in order to get this claim. In order to get this claim. There is a claim, this claim. If psi is not onto, then for any z naught, there exists a psi 1 such that modulus of psi 1 prime at z naught is strictly bigger than modulus of psi prime at z naught. Okay, alright. So this we have shown. You know, last time when I taught this many years ago, I remember recalling reading, a nice metaphor. I thought it's Conway, but I couldn't see it when I searched yesterday. Quickly, I couldn't see, but it has to be Conway or Rudin, because I don't think I ever read any other book on this part. So I couldn't read it yesterday. So from memory, one metaphor to keep in mind in order to do this is, see, in one variable real calculus, what does derivative signify at a point? So there are physically, it signifies two things. No, one is tangent. Right, what is derivative at a point? It is the slope of the tangent. Yeah, for a curve. I'm talking about basic one variable real calculus. Or in physics, it is the velocity, right? If you take the modulus, it's a speed. So you can think of this like, this is what I remember reading. So you can think of this like the speed. I mean, this is just a metaphor to keep in mind. Okay, some analogy to keep in mind. So you can think of this like the speed. So what does this say? If psi, see, remember that we have to show that psi is onto. I mean, there is a psi which is onto. If something is not onto, then given any point, think of this like the speed of that function. The function is moving fast in taking hitting points in u. Right, a function, I mean, it's just a picturization. A function is taking a lot of points in u, and think of this like the speed of that function at that point, at that particular point. And then pictorially, I mean, in this metaphor you can imagine, right, what are the chances of the function hitting all the points, function becoming onto. If it moves fast enough, it should hit all the points, right? So that's the pictorial way of thinking about it. So if you see it somewhere, please give me the reference. Maybe it's Conway only, but I couldn't see it yesterday. But I do remember reading this. I mean, I cannot come up with that kind of a nice analogy in any case. So the point is, if you can maximize the speed, if you got this particular speed at this point, but you can get a function with higher speed, then chances of this becoming onto is more. And if this is not onto, you can get another function with a higher speed. And you can go, so take the function with the highest speed at each point. That's where the complex analysis strength is going to come. We are going to use normal families and all that in order to show that there is a function which will hit the supremum of these speeds. And that function has to be onto, and this is a picture to keep in mind. As you increase the speed, it is going to hit more and more points. So if you can find a function with the highest speed simultaneously everywhere, it has to be onto. Okay, but another crucial point is, by doing this construction using normal families, when we pick up that, when we construct a function which is onto, we might lose oneness. There's a possibility. While doing that mechanism using normal families, when we construct the function which we will make sure it is onto, we might have lost oneness in that process, but we will show using Roche's theorem that look, oneness is not lost. So that's how you get a 1,1 onto function, and that will finish the proof. So my request to all of you, the speed analogy, if you see somewhere, please let me know the correct reference and I will put it here. So yeah, so we have come here. So this is the speed increasing thing rigorously proved, yeah, using Schwarz's lemma. So observe that sigma is a normal family. Why is it a normal family? Sigma is functions 1-to-1 on omega valued in U, holomorphic functions. And you know that in Montel's theorem, you will get normality if you have locally uniformly bounded. Given a compact subset of omega, you wanted uniform boundedness there on that compact set. But we have much more. We have globally uniformly bounded, right? Because everything is valued in U. So everything is modulus less than 1. So therefore Montel applies and sigma is a normal family. So fix a z0 in omega and you consider mod psi prime at z0, these speeds, as psi varies, and consider the supremum and call it eta. So the point to note is that this supremum exists. This supremum exists. Do you see why this supremum exists? Because Rudin doesn't give a justification, and I thought of one way, but I'm just trying to see whether that much is required. Do you see why this supremum should exist? So you are fixing a point, you are taking the derivative at that point, you are taking the modulus, and psi is varying over sigma. So supremum as psi varies over sigma. Okay, so what did I write here? I've written, okay, so I haven't given an explanation here. I have just said that the supremum exists. So try to give an argument for this. I think this should follow, maybe there's an easier argument, but certainly it should follow from the fact that it's a normal family. Sigma is a normal family. So normal means what? Every sequence has a subsequence that converges uniformly on compact sets. So certainly this is true, but we haven't discussed those things. But I let me just give one word. Okay. So what you can show is continuous functions on omega, right? So holomorphic functions are in particular continuous. So sigma is contained in continuous functions on omega, valued in C, in fact. And continuous functions on omega is in fact a metric space. It's in fact a complete metric space. You know, you can give a precise metric and it's a complete metric space. And considering sigma as a subset of that, that sigma is a normal family is same as saying, right? Normality is very similar to sequential compactness. No, what is the difference? In normality, the limit, the subsequence converges and that limit need not be part of sigma. Whereas if something is sequentially compact, limit is included. So this metric that you put on continuous functions on omega is such a metric that the convergence is actually compact convergence. Convergence in that metric is uniform convergence on compact set, meaning Fn converges to F in that metric is same as saying Fn converges to F uniformly on compact subsets. So this is the correct convergence in the holomorphic category. So so the point is sigma being normal is same as saying the closure of sigma is compact. Sigma bar is compact. So if you take psi from sigma, it's contained in a compact set. Yeah, but even there the bar only is compact. So somehow, you know, you are going from a compact set to, yeah, you are varying. So take psi in sigma bar, then the supremum certainly exists, right? Psi in sigma bar is compact. Consider the continuous map psi going to modulus of psi prime z0. So supremum should be attained. But maybe there's an easier argument. So anyway, think about it. So supremum exists, this we need. And by the claim we proved, meaning the claim about the speed, if psi is not on 2, then there is a psi 1 such that psi 1 prime at z0 modulus is strictly bigger than modulus of psi prime z0. It follows that any h in sigma for which modulus of h prime z0 is equal to eta, this supremum. has to be onto. Agree? Yeah, so okay, so earlier I made a mistake. Maybe I said at all points. You don't need to consider all points. Considering one point is enough. That was the strength of our claim. Take a point z0 and consider this. Suppose you have a function which attains a supremum. Mod h prime z0 is eta, then this has to be onto. Why? Because if it is not onto, I can construct a function whose derivative at z0 modulus is strictly bigger than this in that family. But that will contradict eta as the supremum. So that has to be onto. So this is what we will do. So we are going to get an h in h omega valued in u with mod h prime z0 is eta, and here we have to use Montel's theorem in order to construct this such an h. We will use Montel's theorem. We will also use OMT once again in order to do this. But while doing that construction, we may not make we might have possibly lost one oneness. So we have to make sure that one oneness is not lost while doing that process. So we check that H we constructed as in showing the existence of is one-to-one, and here we will use Rouché's theorem, and that will finish the course. Okay, so this we will do in the next class. So that's the lecture part today. We have some time, and we will just talk about general things and continue next time. So I can stop sharing the screen. And let me also stop the recording. So also maybe download the attendance. Okay, good. So I'll stop this recording and start the new recording. Yeah.